How are you, class? Welcome to today's series, which is our introductory for probability and statistics. I am your facilitator for the day, Miriam Kaloki. I hope that you'll be able to follow through the class. Wherever you have questions, remember to just go back to the recording and listen in again. For the summary of our outline for probability and statistics, we'll look at the introduction to statistics. We'll look at sampling methods, probability distributions, moment generating functions, and the difference between continuous and discrete parametric distributions. So we first start with a bit of theoretical work before we begin our calculations. So what is statistics? Ideally, statistics is a mathematical science. But then again, its definition is actually a process whereby it's a process where we collect, analyze, interpret, and present data. Now, in statistics, there are several things that we need to be conversant with. I'm aware that in your class you've not come across statistics in any other place. This is your first time, so we need to have more details on what statistics means. It is largely divided into two. We have what we call descriptive statistics and inferential statistics. For descriptive statistics, we are looking at features of data that is represented in values or graphics. Inferential statistics, we are looking at conclusions, or rather we try to infer what the descriptive statistics are saying. Now, terminologies that will come up will be used through and through include population. Of course, population, we are looking at a large collection of objects, individuals, items, and so on, which from the population we get another terminology which is called the sample. A sample, we describe it as a collection of a small number representing the population. Then we have parameter. In our case, parameter is a summary number like average, percentage, and so on. We also have a statistic. A statistic, we can equate it to the parameter, only that the parameter represents the population and statistic represents the sample. So if you calculate anything using the population, whatever you have calculated will be a parameter. If you calculate anything using the sample, which is a representative of the population, then whatever we have calculated will be called a statistic. Through and through, we use data, but what does data mean? Data is actually a collection of facts or figures or information. Now, data is largely divided into two categories, which we call qualitative and quantitative. Qualitative data qualitative data is non-numeric. In this sense, basically meaning it represents what we call opinions. It can be categorical. So if I was to be asked how I like the weather today, then I can say poor, fair, good, better, best. Those are my categories. Then pick one. That becomes qualitative data. Quantitative data, which is the other aspect of data, or the other group of data, is numeric. Now, with numeric data, it's divided into two. We have continuous and discrete data. Continuous data is data that lies within a particular range. So if I have 0 to 1, the data in between will be accommodated by continuous data. That is 0.1, 0.2, and so on until we get to 1. Discrete data is countable data or finite values. In this case, we are looking at whole numbers. So we have 0, we have 1, 2, 3, and so on. If we were to describe apartments, we have 10 apartments, we don't have 10 and a half apartments, no. So we have data that is discrete, data that is continuous. Of course, this data has levels of measurements, which we largely divide as nominal, ordinal, interval, and ratio, whereby nominal data have no order, ordinal data have order, interval data has meaningful intervals between measurements, and ratio, of course, ratio data has the highest level of measurement, whereby ratios between measurements have intervals as well. But what are the types, or rather the sources of data that we have? We have two main sources of data. That is primary. Now this one we can start a bit of writing. That is primary and secondary. For primary data source, we are talking of, we are referring to the collection of data, first-hand data, with an interaction with our interviewers or the people that we are collecting data from. We actually go to the ground to pick this data. Secondary data is actually data that is already recorded. So we are not the first time people to collect it. Instead, we come in as a second party to just borrow what has already been collected. Thus, we refer to it as secondary data. Now, how do we collect data, whether primary or secondary? For primary, as we have said, you need that interaction with your interviewer. So we have what we call face-to-face interviews. We have telephone interviews, online questionnaires, we have focus groups, we have observations. Of course, we understand from observation, you just need to be present with the particular sample that you're looking into researching. Be present, be there, don't ask any questions, just observe, then collect your data as you learn on how your particular sample is working. Focus groups, of course, we have a group of collective individuals whereby you ask questions, then without any judgment, any individual can be able to answer the question that you have. For secondary data, the sources would be any published sources or unpublished sources. Now with published sources, we have an institution that actually houses a lot of data within the country, which we can use because it is authentic data. They have done large surveys, and this institution is the Kenya National Bureau of Statistics. So if you have any research you have in mind, then go through what surveys they undertake and be able to find out what they actually offer. Now, having known about data, there's a way we can organize it. I know you in your elementary, you have gone through this, but just as a reminder, we can organize data in graphical displays, which include pie charts, bar charts, scatter plots, and so on. So with that in mind, you're able to work around your data to understand it. We have talked of sample. We are saying that it is a small representation of the population. Being researchers, we are limited in terms of resources, labor, time, and so on. So that means every time we are carrying out a research, we must be able to pick out a sample that represents our population in order to study that sample. Once we get our solutions, or we get what we are looking for, the results of our analysis, we can conclude the same for our population using our sample. So that poses our next interest. Our next thing that we want to look at is sampling methods. How am I able to pick out that sample and be able to study it? Of course, the challenges that we have are, one, you don't want to pick a sample that will give you the wrong data, because imagine yourself as a researcher, you have gone to the field, collected data, but at the end of the day you realize it is data that you cannot work with, simply because you got whatever you picked was not right. Now in this case, having spent your time, your money, and incurred a lot of workman labor, that means you cannot start going to redo the survey again. You will tend to work with what you have and use it as best as possible. To make sure such errors don't occur, when we are looking at sampling methods, the one thing we want to deal with is biasness. We want to make sure that as much as possible we reduce it. So sampling methods refers to actually how we select our sample from the population. We have several types of sampling methods, which I'll introduce in terms of the categories and talk about them a bit. We have largely two groups of sampling methods. We have what we call probability sampling, okay, and what we call non-probability sampling. So each of these two has several methods that are in line with it. For probability sampling, we have simple random sampling, we have systematic random sampling, we have stratified sampling, and so on. So if I may explain, with probability sampling, the different sampling methods, which we have said are simple random sampling, systematic random sampling, stratified random sampling, among others, if you note correctly, all of them have random included in the sampling name. Random meaning what? Every time we pick out this sample, it has to be random enough to ensure that there is no biasness. How do we go about conducting simple random sampling? Now this is very simple. We just need a group of our population. So let's say we have our statistics class, it has 40 members, which is our population. We only want to pick out 10 to study in order to conclude for the 40. So we get a stranger who is not conversant with that class. We just tell them, pick 10 individuals for us. As they pick them, because they are not conversant, then automatically it implies randomness. They are not conversant with those people. They just pick whoever is picked. So in simple random sampling, what we are saying that each unit has an equal chance of being in the sample. When we come to systematic random sampling, what happens is this. Just as the name, systematic. There's a system that we are following. Now, this stranger of ours, we let them know. Get to the class before the students start coming in. So what happens? We inform them that the first student to enter will be our sample number 1. Okay? Then count 3 students. The 4th one, let them be our sample number 2, and so on. So the stranger will just come into the class. Whoever comes first, because I'm sure none of you call each other to organize for how to get to class at the same time, all of you will be coming in randomly. So we don't know, we have no clue on who will be the first person. So that first person, as they enter, they become our first sample. Systematically now, we are having an interval of 3. So 3 get in order for us to sample our number 2 sample, and so on until we get to our 10th sample. Remember, we have 40 as our population. We want 10 to represent them. So after every 3 that pass, we pick a sample. We pick a sample and so on until we achieve our 40. So we are saying systematic random sampling requires the target population to be ordered. That is, you use skip interval to pick a sample. I hope we have that correct. Now, next is what we are calling stratified random sampling. Stratified random sampling. Remember, randomness is still there to make sure that we deal with biasness. Now, with stratified, it tends to, we have different groups actually that are in stratas. A good example would be our country right now has how many counties? Yes, you got it right, 47. So each of the county, if we wanted now to sample from all counties, the 47 counties become 47 stratas. 47 stratas. Okay? So each of these groups, now, each of these 47 stratas, we have, if our target sample is 2,000, we have to proportionately, depending on the population in each strata, pick out a sample which, when we add all of them, will amount to our intended sample of 2,000 people. So we've stratified, as we are saying, the group, the population is in stratas, yeah? We have a small example there. We have 5 stratas. So my population is in 5 stratas. I need to pick out people from these stratas as my sample. So proportionately, as we are saying, because one county could have many people, though a small area, or another would have a large area but with a small number of people. So that means you have to pick your sample proportionately in terms of the number of individuals that make up the population. Once that is done, or rather the process of doing that, as long as you have identified your stratas, now how to pick, you apply now the randomness. Just pick without any bias, just whoever is picked, because you have already said that simple random sampling, everyone has an equal chance of being picked to be a sample. So now we employ the simple random strategy in order to get our sample. We come to the next type of our sampling method, which is the non-probability sampling. And the non-probability sampling has several categories. We have convenience sampling, we have judgment sampling, we have quarter sampling, and we have snowball sampling. So this I'll just explain. For convenience sampling, we talk of convenience sampling where population elements are sampled simply because they are in the right place at the right time. Then we have judgment sampling, where population elements are selected because the researcher believes they meet the requirements of the study. We have quarter sampling, where a sample is drawn such that certain important characteristics of a population are represented proportionately in the sample. Then snowball sampling. Sampling relies upon respondent referrals of others with similar characteristics. Now, the fourth one sounds very familiar. In our current situation in the country, if you are found to be infected with COVID-19, then everyone who came in contact with you, per se in our case, our referral, is picked in order to be tested. So ideally, that would go for snowball sampling. So that said, now we introduce we introduce probability, which will be a bit involving because now we have to calculate even as we proceed. So what is probability? What do you think probability is? Okay. In layman language, if we talk about probability, we can say that it's the chance of an event to occur. Okay? Now, if we push it mathematically, when calculating a probability, of course, we want to ascertain to what degree that event can occur. Numerically, when calculating probability, the values range between 0 and 1. What does this mean? If you calculate probability, you get any value over 1 or beyond 1, then automatically you know something is wrong, because probability once calculated, the values should only range between 0 and 1. So how do we go about determining probability? If our class of 40 students, we had 15 of them being females, then if a question is posed to us on what is the probability of the number of ladies in the class, that would mean for us to calculate probability, our probability would be favorable outcomes over, or rather divided by, the total outcomes. Okay? Now, in our case here, total outcomes is the total number of the class, which already we know is 40. Favorable outcomes is the probability that we are looking for, the number of ladies in the class, which we established is 15. So the probability of the number of ladies in the class will be 15 over 40. Now, there are common terms that we come across in probability. One is event, which we through and through in probability use. An event is described as a possible outcome of an experiment or a result of a trial or an observation. Now, these events can be mutually exclusive. What do we mean by mutually exclusive, which is another term that we use in probability? Mutually exclusive event simply means when one event occurs, it stops the other one from occurring. We'll take an example of a coin. A coin has two sides, the head and the tail. If we flip it once, we can only get one result, either the head or the tail. If I flip it and get the head, automatically the occurrence of the head stops the tail from occurring, which now becomes a mutually exclusive event. We also have what we call independent events. Let's use the same example of tossing a coin to explain what independent events are. If I take the same coin and flip it several times, what happens? So the first flip, I get a head. The second flip, I get a tail. The third flip, I get a tail, and so on. You realize that after the first tossing of the coin, whatever outcome I get does not interfere with my second tossing. Whatever outcome I get in the second does not interfere with the third outcome of the tossing. So what does that tell us? That the occurrence of an event does not stop the occurrence of other events, which clearly defines what independent events are. Now we have some rules of probability in terms of our calculation. With probability, you need to be very keen in the language used in any case that you're handling, because the language can be a bit tricky if you don't understand. You will think that you have calculated the correct thing. You'll actually get a value that is between 0 and 1, but the interpretation will have been wrong. To avoid that, then we need to understand some of the rules of probability. We'll look at the first rule. The first rule is what we call addition. Addition rule. Okay? Now, what does addition rule mean? So we are told that this rule is used to calculate the probability of two or more mutually exclusive events. Now, probability questions tend to be formulated as sentences. How will I know that a particular question requires me to use the addition rule? Now, it's very simple. If you get any question that uses the conjunction or, okay, that uses the conjunction or, then automatically, mathematically, you translate it as addition. Mathematically, you translate it as addition. Let's take, for example, a die. A die has how many sides? Got it. 6. 6 sides. And each side has a value on top of it. Now, the value does not dictate the probability. No, no, no. It's the number of sides that we have. So if it's 6 sides, the probability of getting just one side is just 1/6. So we have an example here. We are told, what is the probability of throwing a 3 or a 6 with a throw of a die? So we are only throwing this die once. What is the probability that we will get a 3 or a 6? So simply, since the conjunction or is used, what it's telling us is that the probability of throwing a 3 or a 6 is the same as the probability of 3 plus the probability of 6. Now remember, 3 is just a value representing one side of the die. 6 is just a value representing one side of the die. And we say the probability of one side of the die is 1/6. So this will be 1/6 plus 1/6, which gives us the probability to be, of course, this is 2/6, which when simplified becomes 1/3. Then we have another rule, which we call the multiplicative rule. Now, how do you go about this multiplicative rule? First, it's defined as a rule that is used when there's a string of independent events for which individual probability is known and is required to know the overall probability. So, in that case, let's look at the same example, only that this time round it's phrased otherwise to accommodate the multiplicative rule. Now, with multiplicative rule, what you need to be keen when you're reading your case is you watch out for the conjunction and. You watch out for the conjunction and. The moment you meet that conjunction, then you know that your mathematical translation of that particular question is to multiply. Case in point, we have an example. What is the probability of throwing a 3 and a 6 with 2 throws of a die? Remember, it's independent, yeah? 2 throws of a die. So in this case, we're looking at probability of throwing a 3 and a 6, which translates to the probability of 3 multiplied because of the conjunction and, which is replaced by multiplication, multiplied by the probability of throwing a 6. Remember, the probability of one side of the die, not the value itself, but one side of the die is just 1 over 6. So in our case here, this becomes 1 over 6 multiplied by 1 over 6, which gives us 1 over 36, correct? 1 over 36, which is very correct. Okay, then we go to the next. Rule, which we call conditional probability. Of course, as just by the name, I know you can already guess which conjunction goes with conditional probability. It's actually if. So if you find your case, the way it is articulated as if somewhere, then automatically you will start considering using conditional probability. Now, when describing conditional probability, what we are simply saying is this, that this is a probability associated with combinations of events. We have several events, but given that some prior result has already been achieved with one of them. Let me translate it in a layman's language. In order for a child to go to pre-primary 2, they must have cleared pre-primary 1. So there's a condition for a child to be in pre-primary 2. They can only be in pre-primary 2 if they have successfully finished pre-primary 1. So there's a condition to go to the next level, which ideally explains conditional probability. Mathematically, we can represent it as, so we have probability, x given y, which we read as probability of x, okay, given that y has already occurred. Given that y has already occurred. So mathematically we represent it as probability, so x given y, to be equal to the probability x intersection y over the probability of y. Now, something I need you to note is that intersection can also be replaced with the conjunction and. So x intersection y is similar to and, which is the conditional probability formula. That is, probability x given y is the probability of x intersection y divided by the probability of y. Let's look at an example, a simple one. I'll read it out so that you can be able to understand and calculate the required. We're told in a competitive examination, 30 candidates are to be selected. In all, 600 candidates appear in a written test, and 100 will be called for the interview. So it's clear this is an interview process where they start with a test, then from the test they go to the actual interview up to when they get the number that they want, which is 30 candidates. So let me read out the question again. We are told in a competitive examination, 30 candidates are to be selected. Not that our intention is to have just 30, but 600 candidates appear in a written test and 100 will be called for the interview. There are several things that we are supposed to answer here. The first one, what is the probability that a person will be called for the interview? The second one, we are told to determine the probability of a person getting selected if he has been called for the interview. And the third one, probability that a person is called for the interview and is selected. So we have 3 questions that require us to work them out in order to get our probabilities. So to make my work easier for my solution, then I'll let A, I've just picked an arbitrary value, A, to represent a person is called for the interview. Okay. And another arbitrary value, B, to be that a person is selected. So that makes my work easier in terms of the calculation. So the first question requires that we get the probability that a person will be called for the interview. Now remember, when we introduced probability, we said the simplest way of calculating probability is dividing the favorable outcomes over the total outcomes. In our case here, we want the probability that a person is called for the interview, and the arbitrary value representing it is our A, person is called for interview. So we are looking for the probability of A. What is our favorable outcomes? Remember from the case study, how many are called for the interview? 100. So our favorable outcome will be 100 divided by the total number of outcomes. For us to get the 100, we had 600 who came in for a written test. So 600 becomes our total outcomes, which gives us 1/6 as the probability that a person is selected. The second question requires us to determine the probability of a person getting selected if, there's a condition there, if he has been called for the interview. So the getting selected is B, okay? Being called for the interview is A. So how do we interpret that mathematically? So this will be probability of B given A, which ideally reads as probability of B, which is a person is selected, given that A has already occurred, that is, a person is called for the interview. Now in this case, we don't have to think much about it because we already have the values for the same. A person is selected, then we know from the question 30 candidates are to be selected. So our favorable outcome there is 30. Of course, the condition they meet is that they have already been called for the interview. And how many are called for the interview? 100, which becomes our total outcomes in this case. So 100, which gives us what? Yes, correct, 3/10. Then the third question, which now will require a bit of clever play with our conditional probability approach formula so that we can be able to achieve it. We are told to find the probability that a person is called for the interview and is selected. So, and automatically I know from the rules, I'm going to use multiplication. Now, let me go back a bit to the conditional probability. The conditional probability was probability, so I'll use this B given A should be the probability of B intersection A, which we said is, our intersection represents and over the probability of A that has already occurred. So this one here, I can as well say that it's actually probability of B multiplied by A or A multiplied by B. Both will give you the same. So probability of AB or BA as you wish. Now, if I want to make this the subject, which is the probability that the person is called for the interview and is selected, then what does it mean? First, I multiply on both sides with probability of A. Okay, so probability of A. So this one can go. So that probability AB or probability BA, it's a product, okay, so will be probability of A. What is probability of A? That a person is called for the interview multiplied by probability B given A, which is the conditional probability that a person is selected given that they have already done the interview. Okay? Now, if you look at probability of A, we have already calculated it and gotten what? 1 over 6. So, 1 over 6 multiplied by, beautiful, probability B given A, we have also already calculated it, which is 3 over 10. So the probability AB, whereby a person is called for the interview and is selected, and for multiplication, if we translate it mathematically, will give us what? So we have 3 over 60, which when simplified becomes 1 over 20. Good. So if you have been able to follow through, you know that the 3 rules of probability are multiplication, addition, and conditional probability. This you need to be very keen because your cases that you'll be handling are normally represented as just a story. This story you have to interpret it very well in order to get the correct thing to calculate. So having had an introduction to probability, it takes us to our next level, whereby we want to look at probability distributions, okay? So we are aware of probability. If I calculate probability, the values I can get should range between 0 and 1. So in that case, even as we introduce probability distributions, we know for each distribution, as we calculate probability, our values will always range between 0 and 1. So we start with, in our class today, we will look at 2 distributions. And these 2 distributions have one thing in common, in that they are discrete. If you remember very well, when it described data, we had qualitative and quantitative. For quantitative, it was later divided into 2, where we had continuous and discrete data. So in this case, we are referring to that, that definition of discrete, whereby we are using finite outcomes or whole numbers, as you may say. In this case, they will start from 0 because we can have a 0 chances of an event occurring. So they'll start from 0 and so on. The first probability distribution that is discrete for us to encounter is what we call binomial probability distribution. Binomial probability distribution. What does bi mean from binomial? Bi means what? 2. You're correct. 2. Now, in this case, for binomial, simply defined, we expect that from our data, our outcomes are 2. Either a success or a failure. So with that in mind, now we can describe binomial very well. That first of all, it is a discrete probability. And by discrete events, we say that these are events whose results or outcomes can be counted. Okay? We have some properties. Among the properties is that the first property, a binomial probability distribution has 2 outcomes, as I've mentioned. It can either be a success or a failure. We'll see it defined well in our formula. 2, the probability of each outcome is independent of the previous outcome. The third one is that the sample size ideally is generally fixed, because once we pick it, that's it. Then another property is that the probability of success and failure, they tend to approach 0.5 if the sample size increases. With those properties in mind, then how do we go about determining the binomial probability? Of course, we use a computational formula. Our computational formula for the binomial will be the probability. So we'll describe each parameter once we are done with the formula. So n combination r multiplied by p raised to power r multiplied by 1 minus p, which is raised to power n minus r. Of course, we need to understand what each parameter there means. Let me start with p. P here, so where p in this case describes the probability of success. Okay, P describes the probability of success. Then what does 1 minus P mean? Quite obvious, yeah? If we have success calculated, then whatever is remaining is failure, because we said we have 2 outcomes, success or failure. And remember, the highest value of probability that you can have is 1, where 1 means that that event must occur. So if we have 1 minus P, which in different texts you can find equated as Q, to mean probability of failure. To mean probability of failure. Of course, our N describes the sample size. Our R describes the number of successes. Our R, the number of successes, is what we are interested in calculating. So number of successes. Good. Having seen the formula, following it through and through. Of course, we have an element here, N combination R. From your calculator, you're able to see N combination R. We know that the value of N should always be greater than R in combination. This I'm sure you have covered in linear algebra. So the assumption is that we already know how to get combinations, we know how to get permutations, we know how to get factorials. So n combination r is part of the formula in getting the binomial probability. Let's exercise this formula through an example. I'll read out the example, then we can follow slowly by slowly. Our example reads like this. A medical survey was conducted, okay, in order to establish the proportion of the population which was infected with cancer. The results indicated that 40% of the population was suffering from the disease, okay? A sample of 6 people was later taken and examined for the disease. We have several probabilities that we want to calculate. That is, number 1, find the probability only one person had the disease. Number 2, find the probability exactly 2 people had the disease. And number 3, find the probability that at most 2 people had the disease. Now let's go back to our case. We are the researchers. What are we interested in? Finding the people in the population who are infected with cancer. What does that mean when defining a success in our survey? It means that if I get a person who is infected with cancer, then that is a success in terms of my research. What does the case tell us? That the results indicated that 40% of the population was suffering from the disease. So my success is defined by 40%. So that means automatically I'm able to calculate my failure. And we also have the sample size that was later taken and examined, which is of 6 people. Now, with that in mind, let's just go bit by bit to understand what we already have from the data. Okay, so from the data, our probability of success, which is P, is what? 4 over 100, which is, that is 40 over 100, sorry, which is 40%. We want to convert it into values that range between 0 and 1 because it's a probability, which gives us, so this is 40%, 40 over 100, which is the same as 0.4. So our probability of success, finding an infected person, is 0.4. What is the probability of failure? It's 1 minus P. P, we already have the value, 0.4. So this becomes 1 minus 0.4, which is 0.6, correct. We have our N, the sample size that has been picked later on to be examined is of 6 individuals. We have everything that we need. Now, each question will define our R. Each question will define our R. The first question, before we do the question, maybe we can define our formula. We have said probability of R is N combination R, P raised to power R, 1 minus P raised to power N minus R. So the first probability of interest is find the probability that only one person had the disease. Only one. Only one means what? My R at that particular moment is 1. So we are looking at probability 1, which is equals to what? So this is, N is 6, so 6 combination 1. What is P? We have already found P to be 0.5. So we are multiplying 0.4, sorry, 0.4 multiplied by 0.4, which is raised to power R. Our R is 1 multiplied by 1 minus P, which is our probability of failure. Our probability of failure is 0.6. So 0.6 raised to power n minus r. Our n is 6 minus 1, which is 5. So 6 minus 1, which is 5. Let me just rewrite this. 6 combination 1 times 0.4. Of course, anything raised to power 1 is still itself. So 0.4 times 0.6 raised to power 5. So if we take our calculators and calculate this, what do we find? Is a probability. Remember, the values should range between 0 and 1. So we have 6 combination 1, which is being multiplied by 0.4, which is being multiplied by 0.6, that's raised to power 5. This gives us, now we'll answer in 4 decimal places so that we can allow for percentage calculation if need be. So in 4 decimal places, this will be 0.1866. The probability that only one person has the disease is 0.1866. Of course, for the layman, they would understand if you tell them there's a chance of, if you multiply by 100, we get the percentage. So this will be 18.66%. So they would understand when you say there's an 18.66% of one person having cancer. Our second probability of interest is exactly 2 people had the disease. Now this is similar to the first one. This is similar to the first one because we are interested in exactly 2. So ideally it's just the probability of 2 infected with the disease, which in this case will be 6 combination 2 multiplied by 0.4. We are following the formula 0.4 raised to power r, which is 2 in our case. So our r here is 2 multiplied by 0.6 raised to power 6 minus 2. 6 minus 2 is what? 4. So let me rewrite that. So 6 combination 2 multiplied by 0.4 raised to power 2 multiplied by 0.6 raised to power 0.6 raised to power 4. Let me just bring you up to speed with something that you should note. If you look at the powers of success and failure, they should always add up to the sample size. So in this case, we have 2 plus 4, which would give us the sample size 6. In the first instant, we had raised to power 1, so 1 plus 5, which still gives us 6. So make sure your powers of success or your order of success and failure, the powers add up to the sample size. So if we calculate that, 6 combination 2 multiplied by 0.4 squared or raised to power 2 multiplied by 0.6 that's raised to power 4. What do we get? In 4 decimal places, we want to make sure that there is continuity in our solutions. We get 0.3110. This is the probability exactly to have the disease. Now we come to our third probability of interest. We are told to find the probability at most to have the disease. What does at most mean? Of course, this is an inequality, so you need to think inequalities here. When talking of at most 2, it means the highest number that you can consider is 2. That means the ones before 2 are also included. Okay? Good. So how many are included right before 2? We have 0, we can actually have 0 people infected. We have 1, we have 2. So at most 2 for an inequality is actually less than or equal to 2. So the third probability of interest is looking at probability at most 2, which is the same as probability less than or equal to 2, which we are saying all values before 2 and inclusive of 2. So probability of 0 or the conjunction or is replaced by addition. So or plus probability of 1 plus probability of 2. Good. So that means we have to get the probability of 1, add to the probability of 2, probability of 0, add to the probability of 1, add to the probability of 2. Now, let me just write it out. I am assuming that I didn't have any other question. Let me, using the binomial probability formula, write each of them, how I'd calculate. So my n is 6. So 6 combination 0 multiplied by 0.4 raised to power 0 multiplied by 0.6 raised to power n minus r, which in my case is 6 minus 0, which is 6. That's for probability 0, plus probability 1. We have already looked at it, but then we are assuming that this is our only question. So let's rewrite it. 6 combination 1 multiplied by 0.4 raised to power 1 multiplied by 0.6 raised to power 6 minus 1, which is 5, plus, I'll continue here, probability of 2. So 6 combination 2 multiplied by 0.4 raised to power 2 multiplied by 0.6 raised to power 6 minus 2, which is 4. So if we get these probabilities, these probabilities, the probability of 0 added to the probability of 1 added to the probability of 2, it will give us the probability at most 2 people are infected with cancer. So let's turn to our calculators and do this very quickly. So we have, I can pick out the values of the others. For the probability of 1, we got 0.1866. For the probability of 2, we got 0.3110. So I need to calculate the probability of 0 people infected. So this is 6 combination 0 multiplied by 0.4 raised to power 0. Any value raised to power 0 is the same as 1. Then multiplied by 0.6 raised to power 6, which gives me, so in 4 decimal places, 0.0467. So 0.0467, I'll add to now the others. So plus 0.1866 plus 0.3110, which gives me, so probability at most 2, once I do the addition, 0.5443. Are we together, class? Quite easy to follow. At most 2 means that you are in an inequality explanation, you're looking at any value less than or equal to 2. So that means you need to have in mind, what does at least mean, what does more than mean, what does less than mean, so that you can be at par with being able to calculate the correct probabilities. Now, as a binomial probability, it also has its mathematical properties. The mathematical properties, ideally, however much it's a distribution, in any of our calculations, we're interested in finding out some simple descriptive statistics, that is the mean, the standard deviation, and also the variance. So for the mathematical properties, for us to get the mean, so mathematical properties, mean, the first one is the mean, which is the same as expected value, would be given by n times p. Now, if you remember well, our description of n was, n is what? Yes, the sample size. Okay, and p was what? P was the probability of success. Probability of success. So in our previous example, if we wanted to get the mean, then it would simply be n, the value of n, multiplied by the value of p, which from example, our mean, our n is 6, our p is 0.4, which gives us what? When you calculate, we have 6 multiplied by 0.4, which gives us 2.4. So our mean in this case would be 2.4. Okay? We have another mathematical property, which is called the variance. Now the variance in this case would be n times p. Now we add times q. Remember what q was? Q was the same as 1 minus p, which is our probability of failure. So let me just define that. Q, which is equivalent to 1 minus p, is the probability of failure. Okay? So if we wanted to, in the same example, calculate the variance, then it would mean our n, which is 6, multiplied by our p, which is 0.4, multiplied by our probability of failure, which turned out to be 0.6, to give us what? So we have 6 multiplied by 0.4 multiplied by 0.6, which gives us 1.44, correct? So this is variance in accordance to the example. Now, by default, if you get the variance, you're able to get the standard deviation, which is another property, which is another mathematical property. So standard deviation, by definition, standard deviation is actually the square root of variance. That's perfect for us because we know variance in this case is n, p, q, which from the example, we can be able to calculate it. We already have the variance, 1.44. So standard deviation, our SD, will be square root of 1.44, and we are home. So if we get the square root of 1.44, it turns out to be 1.2. And there we have seen the mathematical properties of a binomial probability distribution. We are able to calculate the mean, we are able to calculate the variance, and we are able to calculate the standard deviation, which concludes the binomial probability distribution. Now to our next distribution, which is our last distribution for the day. It is still a discrete distribution. It is a very interesting distribution because it has some uniqueness in it. This distribution is called the Poisson probability distribution. The Poisson probability distribution. So already we know it's a discrete distribution. That means our outcomes are whole numbers. Okay? Now, being a discrete distribution, the unique thing about Poisson distribution is that it describes events that are termed to be rare. What do you understand by rare? Something that is rare means that if we are observing, it will take a long time of observation for that thing to occur. Okay? To understand it further, it's as simple as this. Anything that is rare, when it happens in our social media world, it makes news. What do I mean by that? If we have, I remember a case a few years ago. Is it a few years ago or a year ago? We had a lady who gave birth to 5 children at once. Can you remember the name? How do you call 5 children born at once? Find out. But what I want to highlight is that particular event, being rare as it is, made news. Okay? So rare events end up making news because we take a long period to observe, for them to be actually observed. Now, Poisson distribution ideally can be related to binomial in that once that event occurs, then it's a success. If it doesn't occur, then it is a failure. So we can relate the two. But we'll see how the relation helps us mathematically. Okay, in businesses, Poisson distribution is actually very important, especially in manufacturing. Every time manufacturing is going on, for a product to be ready for the market, then the quality control person must make sure that it meets the standards, okay? If it doesn't meet the standard, automatically it becomes a defective item. So imagine you have gone to the supermarket, you're reaching out for your favorite margarine. I'm assuming it's Blue Band. You're trying to buy 500 grams, only to get home and realize the contents inside are 250 grams. What do you do in such a case? Automatically, you'll have to go back to the supermarket and try to complain, return, to be refunded, okay? Now that's a rare occurrence because if the quality control person is present in the process of manufacturing and also packaging, they will know very well if the conveyor belt is passing with the containers for 500 ml or 500 grams, they should make sure that the contents being poured are also 500 grams. If at all there's a problem, how do they identify it? The quality control person just picks a sample of the production, checks whether they meet the standard. Once they pass the exam of meeting the standard, then automatically they can be distributed for selling. So if they are not okay, then the quality control will actually be alert on either the functioning of the machine is not okay, or someone forgot, who had a night shift, to put the right containers on the conveyor belt. So it speaks a lot. They are able to identify anomalies. That said, what is the formula that we use to calculate Poisson probability? The formula is as follows. We have probability x being equal to exponent negative lambda multiplied by lambda raised to power x, where our x is the success here, divided by x factorial. Of course, we need to explain what each parameter means. Starting with x, of course, x is our number of successes, yeah? Number of successes, that is what we are interested in calculating. our lambda refers to actually mean, okay, mean number of successes. Our exponent, this is a value that you can get from the calculator. So however much we represent it here, you only need to pick the exponent character itself on your calculator, which is approximately 2.718, of course, and so on. We have a challenge. How do we get the value of the mean? So that means before we can even calculate anything, we need to understand the mathematical properties of a Poisson distribution. Now, they are very simple because they are unique. Mathematical properties. This is where the association with the binomial comes into play. Remember, we said that if the event occurs, we'll associate it with the binomial in the sense if the event occurs, it's a success, which we know from binomial, it's P. If it does not occur, it's a failure, which we know by binomial, it's 1 minus P. So for mean, which is represented by lambda, borrowing from binomial is actually n times P. Now the unique thing about this distribution is the fact that once you calculate the mean, you have also calculated the variance. So what does that mean? Variance is also the same as lambda, which is n times P. So that makes our standard deviation to be square root of lambda. So in any case or question that you're given, the first thing to calculate in order to enable you to proceed is the mean number of successes. We have said the exponent, we are able to pick out the character from the calculator directly. Number of successes ideally speak to the probability in question. So once we know the value of lambda, then automatically we are able to look at an example. Let's try this out as an example to understand further what our formula means. I'll read the example, then we can follow through. We are told a manufacturer assures his customers that the probability of having a defective item is 0.005. A sample of 1,000 items was inspected. Find the probabilities of having the following possible outcomes. The first outcome, that only one is defective. The second outcome, that at most 2 are defective. And the third one, more than 3 are defective. Now, let's look at this. We are already saying that there's an assurance the manufacturer is letting people know, who are his customers, that for someone to get a defective item, it will take a probability of 0.005. And of course, the manufacturer is concerned on getting the defective items. So this becomes our probability of success. Borrowing from binomial, it's our P, 0.005. Now, the sample size here is large, 1,000. How do you differentiate Poisson and binomial? If you look at Poisson, the probabilities are very low, and the sample size is very large. Meaning what? It takes a long period of observation to experience the event. That's why sample size becomes large, probability becomes small. Now let's, our question requires that we find the possible outcomes that only one is defective, or at most 2 defective and more than 3 defective. From the formula, probability X which is equals to exponent negative lambda multiplied by lambda raised to power x over x factorial, we need to first find lambda. And our lambda in this case will be, as seen from the properties, NP, which is 1000 times 0.005. Okay, so from our calculators, 1000 times 0.005 gives us 5. So we have the value of lambda. Imagine with the value of lambda, you're able now to calculate very easily because you're substituting the parameters that are required. In our first question, we are looking at the probability of what? Only one is defective, so just one. Okay, so our value of x there is 1. That means it will be the exponent negative 5 multiplied by 5 raised to power 1 over 1 factorial. Okay, so as we said, from your calculator you can actually get exponent. So just pick out exponent negative 5 multiplied by 5 raised to power 1, of course, is 5, and 1 factorial is just 1, which gives us 0.0337. We'll stick to 4 decimal places. So this is a probability that only one is defective. The next one tells us to find at most 2. We have previously seen what at most 2 means. The highest value we can have is 2. So we will consider anything that is 2 or less than 2. In our case here, we can have actually 0 items that are defective, 1 item that is defective, or 2 items that are defective. So we are looking at probability less than or equal to 2, okay? Which is the probability of 0, or which translates to plus probability of 1 plus probability of 2. So once we calculate that, let me just put in as expected. So exponent negative 5 multiplied by 5 raised to power 0 over 0 factorial. 0 factorial is actually 1, plus exponent negative 5 multiplied by 5 raised to power 1 over 1 factorial plus exponent negative 5 multiplied by 5 raised to power 2 over 2 factorial. What does this give us? We already have for 1. So let's see what the others give us. Exponent negative 5, okay, multiplied by anything raised to power 0 is just 1, okay. So this gives us 0.0067 plus, we already have calculated the 1 for 1, 0.0337 plus, so we calculate probability of 2 defective, so exponent negative 2, exponent negative 5, exponent negative 5 multiplied by 5 raised to power 2, which is 5 squared. 5 squared, of course, we know is 25. Okay. Divided by 2 factorial. 2 factorial is 1 times 2, which is 2. Okay. So which gives us 0.0842. 0.0842. So we can add the rest and see. Okay. 337 plus 0.0067. So this gives the probability at most 2 to be 0.1246. The last one, but not least, we are looking at the probability more than 3 defective. More than 3 defective, what does that mean? It means that we need to consider the probability of 4, 5, 6, up to 1,000. Surely. It will take us the whole day to calculate up to 1,000. So we need to cleverly approach the probability of more than 3. We know that if we add all probabilities from 0 up to 1,000, they should all add up to 1. Okay? So with that in mind, more than 3 means it is anything beyond 3, so from 4. In our case, probability greater than 3 will be defined by 1 minus now the probability that you can be able to calculate, okay? So greater than 3 does not include 3. But what is before that? We have probability of 0, probability plus probability of 1 plus probability of 2, okay, plus probability of 3. Good. Okay? Very clever, because we know 1 will be as a result of calculating all probabilities from 0 up to 1,000. Now this one we can easily do so. Up to probability of 2, we have previously calculated. So let me just write the summation of these three, 0.1246 plus now the probability of 3, which in our case will be exponent of -5 multiplied by 5 raised to power 3 over 3 factorial. Okay, so what do we get here? So let me calculate that. We have exponent -5 multiplied by 5 raised to power 3. Okay. Then divided by 3 factorial. 3 factorial, of course, is the multiplication of the factors 1, 2, and 3, which gives us 3 factorial is 6. So divided by 6, which is 0.1404, 0.1246. Okay. So 1 minus the summation of this, what does it give us? 0.1246. Okay, so 1 minus the summation, which gives us 0.7350. So probability greater than 3 defective would be 0.7350. It is my hope that you have followed our class, because this brings us to the end of our class today. If at all there's a place you have not understood, kindly replay and get to understand the concept. Make sure that as you're listening, you have a pen, a notebook or a paper, and your calculator in order to be able to follow. See you in our next class. Thank you.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.